Okay, so one other thing I want to talk about here with filters is that there are two what we'd call main types of filter. I don't know if I want to say types. Well, let me just put it this way. There are what's referred to as passive filters, and there are what are considered active filters. Now, the simplest way to think of passive filters is that they only contain resistors, capacitors, and inductors. Active filters will contain resistors, capacitors, inductors, but then they also include transistors, usually in the form of an op-amp. So we usually aren't going to have discrete transistors sitting there, but we have an op-amp, which an op-amp is made up of transistors. So that's why it's considered an active filter. So that's the main difference between it. We're going to start with passive filters. And before we even get started on this video, we're not going to even start on the equations for like a low pass or a high pass or looking at a circuit just yet. We're going to have to, first off, define what we mean by cutoff frequency. Now, before we do that, I wanted to show you a picture here. So this picture here is just from, well, I don't know where this is from, Signal Processing Stack Exchange. This is a picture of a low-pass filter, but it has what's called different orders. Because remember, we said we never get the ideal case. So this blue curve here is showing what's called a first-order filter. And you can see the first-order filter doesn't very much look like the ideal case. Now we're going to start with first-order filters, of course, because, well, sometimes they're good enough, depending on what your application is. And second off, of course, they're the easiest ones to start with. But then we can increase the order of the filter, which essentially corresponds to putting more poles in. We'll see that for a low-pass filter, it's going to have a single pole in the denominator. And remember, we said that poles are going to come back and play an important role in filters. And so that's one of the reasons we're going to be looking at the poles. Now, as we increase the order, we're essentially increasing the number of poles in the denominator. And we can see this is well, I just went to the thing here. Let me go back to the picture here. I won't click on it. You can see the green one is a second, the red is a third, and the black is a fourth. And you can see the higher the order, the more we are approximating what the ideal filter would be. Now there's trade-offs to doing higher order filters. Circuit complexity becomes a big issue. So what you'll learn in the advanced filters class is when you'll be given a filter spec, you'll often be given maybe a cutoff frequency, but you'll also be given here like what kind of drop-off do you need? Like how fast do you need this filter to drop off? You notice this blue filter is not dropping off that fast, but the black filter is dropping off quickly. And there will be a way to determine what order of filter you need based off of what kind of drop-off you need. So that's important. Now, for this course, of course, we're going to keep things a little bit simpler. So we're going to first just examine. We're going to examine first order filters so we can truly understand how to analyze filters and design filters and look at some higher order filters. We're not going to look at a ton of higher order filters, but we are going to look at some. And so that's what we're going to be going for. Now the next thing here is we have to define what we mean by cutoff frequency. Now, the short answer to this, which we'll go into the details on why we choose this here, is if I'm looking at a low-pass filter, and I say here's the cutoff frequency, and this is 0 dB, this corresponds to minus 3 dB. Now, sometimes people want to think, well, that's not very low. You know, it's that doesn't seem like, because, you know, like, wouldn't you want the cutoff frequency maybe like over here or something? Because, you know, then I'm down at like minus 20 dB or something like that. Well, we have to understand, first off, how we compute decibels, and also understand that this is a log scale here. So if you're talking about having this be the cutoff frequency for something like maybe over here, you're talking an order of magnitude often in as far as the difference in frequency. So let's look at, first off, how we define decibels. Now this is the first thing that's important. If you're given a power here, the power is converting to decibels is 10 times the log of the magnitude of the power. And when we say log here, we're referring to the common log. So some textbooks emphasize that, putting log base 10. I'll go ahead and do that as well, because sometimes we look at log just as the natural log. For instance, MATLAB does that. There's reasons for that. I won't go into the details here. But then if we're given voltage or current decibels is equal to 20 log base 10 of the magnitude of, well, I'll just say voltage in this case, but it could be current as well, depending on what you're looking at. Now, the first question people often come up with is, why with power do you do 10 and why do you do 20 with voltage? And it's a very simple explanation. Just go back to circuits 1, purely resist a circuit, and let's just look at the power. Well, we know power is voltage times current, but then let's think about this in terms of just voltage. This would be voltage squared over resistance. Now, resistance, I know that's a number, but what do we have here? Voltage squared. So if I'm wanting to think about this being decibel for power here, well, if I have power here and I wanted to basically just substitute voltage in, and I know there's the resistor, don't worry about it, but it's, if I'm wanting to convert voltage, because I'm not computing power necessarily, but if I'm wanting to do voltage here, well, if I'm defining power to be 10 log base 10 of P, it would make sense then that we would define dB equaling 10 log base 10 of the magnitude of my voltage squared, because that's what you have to do to voltage in order to get power. But then a simple log property shows us, oh, well, what do we do here? That's just 20 log base 10 of the voltage. Okay. So now here we're going to do a definition, and we're just going to do this as a definition here first, and then we'll see why we do this particular frequency here, why we use this particular why we use this particular definition. So the cutoff frequency is defined as h at j omega c, magnitude of that is 1 over the square root of 2 H max. And I'll say magnitude of H max. Now, why is it 1 over square root of 2? Well, we'll look into that in a second here. But first off, I want to show you then why we look at the minus 3 decibel here. So let's assume H max is 0 decibels. So I'm having to do 1 over the square root of 2 of that. Is that what I want to do? No. I don't want to say H. I mean, that's what I want to do, but that's not the way I want to phrase it. Let's first just go ahead and what we're going to do is we're going to convert this to decibels. And we're going to do it assuming H at S is V out over Vn. Now it doesn't really matter whether it's V out over Vn or not. It could be I out over In, it could be V out over In. It doesn't matter. I'm just assuming that for easiness sake. And the reason it doesn't matter is the point of which decibel formula do we use. Well, in this case, no matter what, we're dealing with a voltage or a current, which means I'm going to do this decibel formula as opposed to this one here. So actually I'll go ahead and convert this whole thing to decibels. And we'll convert this whole thing to decibels here. So we'd have 20 log of H at j omega c. So I'm just going to write this, you'll see what I do in a second, is equal to 20 log of 1 over the square root of 2 times H max, magnitude of H max, and then what do we have here? Well, I'm going to just write that we have this instead as H at j omega in decibels. And this would be, now I'm going to use some trig properties, 20 log of 1 over square root of 2 plus 20 log H max. Now we'll do this assumption here. Assuming unity gain, H max is equal to 1. So 20 log of 1 is 0. So now I just have to compute here. This is just some number that I compute, and you can go through the computation. I encourage you to do it on your calculator just to prove to yourself that this is true. Technically, you get minus 3.01 decibels. Actually, I'll even put a few more out here. 3103 decibels plus 0 decibels. Minus 3 dB corresponds to cutoff frequency. Now we might want to be a little bit more careful here. And what do I mean by a little bit more careful? We should really think about this is that the cutoff frequency omega c is minus 3 dB from the max H max in decibels. Because when we start getting into active filters, you might have that the magnitude of H max in decibels, maybe it's, I'm just going to pick a random number, let's just say it's 17 decibels. So then omega C would correspond to the point where we are at 14 decibels. It's not always -3, it's -3 from the maximum. And so if we were to look real quickly at a plot of this, the idea here, I mean the plot's going to look exactly the same as the other ones we've drawn, we're just going to label something different. So we got this here, we'll label this as omega C. Looks exactly like the other low-pass filters, but instead of this being labeled as 0 dB, this would be 17 dB because that's the H max, and then the -3 dB point here would be 14 decibels. So that's important to recognize here. Now, in passive filters, which is what we're going to be spending the next several videos on, the next several lessons on, passive filters always have a max gain of 1. So that's why we can always just think of it as the -3 dB point. Now, we're going to end this video here. We still haven't talked about why is this defined for h at j omega c being 1 over the square root of 2 of the transfer function. And we're going to come back to that in the next video.